I want you to just take a second right now and look at your hand.
Yeah, literally physically look at it.
Right, really look at it. Notice the intricate network of veins, the texture of the skin, the actual physical weight of your own body occupying space in this exact moment.
It feels incredibly solid.
It does. It feels permanent. And now I want you to think about the night sky. Like whenever you step outside on a clear night, away from all the glare of the city lights, and you look up at that huge expanse.
There is this almost unshakable sense of permanence to it.
Exactly. The constellations you see up there, those are the exact same patterns that ancient humans used to navigate the oceans thousands of years ago.
Right.
And because the cosmos looks so incredibly stable, so immutably fixed when we measure it against the microscopic span of our human lifetimes, we naturally fall into this cognitive trap.
We assume it's just a permanent structure.
Yeah, we assume that it simply is. But what if everything you see, I mean, every single shining star, every swirling spiral galaxy, and yes, even the very atoms that are currently holding your hand together, what if all of that exists within a strictly temporary passing phase of cosmic history?
It's a terrifying thought at first.
It really is. What if the universe as we know it is nothing more than a fleeting thermodynamic season in a much longer, unimaginably darker cosmic year?
You know, the human brain is essentially this pattern recognition machine, and it has been aggressively optimized by evolution for a roughly 70 to 80-year life cycle.
Right, which is nothing on a cosmic scale.
Less than nothing. We are deeply trapped in our own localized temporal bubble. I mean, we measure time in days, we measure it in financial quarters, maybe in centuries, if we were reading history.
Yeah.
But to actually grasp the reality of the physical systems we inhabit, we have to fundamentally break that cognitive scaling. The universe operates on timescales that make the entire sum of human history, from the very first controlled use of fire all the way to the launch of the James Webb Space Telescope. It makes all of that look like a rounding error.
Just a tiny blip.
Exactly. It is a profound shift in perception. It forces us to stop viewing the universe as a static backdrop and start viewing it as an active, decaying engine.
And that is exactly why we are here today. Welcome to this special Crisis in Perception edition of our Deep Dive. If you are new here, this project is entirely focused on examining the underlying systems that shape our world, our beliefs, and really our perception of reality itself.
We take a systems-level approach to big questions.
We do, and today's Deep Dive explores a massive, somewhat existentially terrifying topic: how the universe will end.
It's a big one.
Huge. But I want to set the ground rules right up front for you listening. We are not going to be indulging in wild sci-fi speculations today. We aren't pulling up Hollywood apocalyptic imagery of giant lasers or, sudden alien collapses.
No, we are sticking strictly to the physics.
Right. We are treating the universe exactly as what physics tells us it is: a massive, unfolding thermodynamic system. A system whose large-scale behavior, from its initial boot up to its final shutdown, follows identifiable, completely predictable patterns. And those patterns are driven entirely by the laws of gravity, nuclear fusion, and the relentless unidirectional march of entropy.
If you strip away the romanticism, the poetry, and all the mythology we've draped over the night sky over millennia, what you are left with is a system governed by strict, unforgiving physical laws.
And that's actually a good thing for our understanding, right?
It is, because those laws are constant. They allow us to trace the system's history and project its future with a startling degree of mathematical confidence. We aren't just guessing here.
So what are we using as our foundation today?
We are drawing on some brilliant source material, specifically the frameworks laid out in Professor Brian Cox's work, How the Universe Will End.
It's an incredible piece of work.
It really is. By treating the cosmos as a closed thermodynamic envelope, we can actually map out the remaining epochs of our universe's life. But, as with any system analysis, to understand the eventual shutdown, you first have to understand its initial conditions.
You have to look at how the system booted up in the first place.
Exactly.
The genesis.
So let's talk about that genesis. We have to trace the architecture all the way back to the Big Bang, which was roughly 13.75 billion years ago. And I think the popular conception of this is usually completely wrong.
Oh, absolutely.
People picture the Big Bang as this giant explosion in a dark room, like a firework. And suddenly, boom, there are stars everywhere and galaxies are just sitting there. But that's not how the thermodynamics worked at all, is it?
Not remotely. What immediately followed the Big Bang was the embryonic period of the universe. This is a phase we call the primordial era.
The very beginning. Right. And for the first 100 million years or so, the conditions were fundamentally hostile to structure. It wasn't just hot, it was a state of supreme thermodynamic density. The universe was a blindingly hot, completely opaque
So
plasma.
you couldn't even see through it.
No, light couldn't travel freely. The ambient energy, meaning the sheer kinetic motion of the particles, was so violently intense that it overwhelmed any attractive forces.
It's kind of the ultimate chaotic state. You have protons and electrons basically ricocheting off each other at unimaginable speeds.
Yes.
Like, if an electron even tried to settle down and orbit a proton to form a simple hydrogen atom, some high-energy photon would immediately slam into it and blast it away.
It's a system with simply too much input energy to allow for any stable bonds to form. It's completely dominated by radiation. Nothing could clump together.
But the universe was expanding.
That is the key variable. It was expanding. And as any closed thermodynamic system expands, its internal energy gets distributed over a larger physical volume.
Which means the temperature has to drop.
Exactly. This is the crucial mechanism. Only after the universe had expanded and cooled sufficiently could a phase transition finally occur.
This is what physicists call recombination, right?
Yes, recombination. The ambient temperature finally dropped below that critical threshold where photons were energetic enough to tear atoms apart.
So suddenly the electrons could actually stick to the protons.
They bound together, yes. The entire plasma neutralized into a vast, dark fog of hydrogen and a little bit of helium gas. And suddenly, the universe became transparent. Photons could fly in a straight line.
Which really sets the stage for the weakest force in the universe to finally do some heavy lifting. I'm talking about gravity.
Gravity is the star of the show here.
Because in that early chaotic plasma, gravity was essentially a non-factor. It was getting completely shouted down by the intense thermal energy. Everything was moving too fast. But once things cooled down, gravity, which is this incredibly patient, persistent force, finally had the leverage to start pulling things together.
It began to amplify tiny microscopic irregularities in the density of that hydrogen fog.
Places where there was just slightly more gas than somewhere else.
Right. Gravity is the ultimate organizer of the macro-universe. It started pulling together the primordial dust, the hydrogen gas, and the invisible scaffolding of dark matter into these immense structures.
The very first galaxies.
The precursors to them, yes. And as those vast clouds of hydrogen collapsed inward under their own immense weight, the pressure in their centers began to rise exponentially.
And with that pressure comes heat.
Immense heat. Eventually, they hit a critical threshold of temperature and pressure, and they ignited. Those early, massive stars initiated the central mechanism that has shaped all of cosmic history since.
That ignition sequence, that first light.
That ignition marked the dawning of the second great epoch in the timeline of our universe.
Okay, let's unpack this, because that second epoch is the exact one you and I are living in right now. It is called the Stelliferous Era.
The Age of Stars.
The Age of Stars and the Age of Light. Whenever you look up at the sky, you are looking at the defining feature of this specific slice of cosmic time. But to really grasp what is happening out there, we have to stop looking at stars as just pretty glowing dots on a black canvas.
We have to view them as systems.
Exactly. From a systems perspective, a star is a highly complex, fiercely active thermodynamic engine.
And what's fascinating here is that a star is not really an object in the way we think of objects. It is an event.
An ongoing process.
It's a dynamic, active process that exists in a state of violent, uneasy equilibrium. To put it in systems terms, think of a star as a multi-billion-year-long wrestling match between two opposing forces.
Let's break those courses down.
Sure. On one side, you have the inward input, which is gravity. The sheer mass of all that hydrogen gas, we are talking billions upon billions of trillions of tons of it, exerts an enormous gravitational pull. It is crushing everything inward toward the dead center of the sphere.
And if gravity were the only variable in the equation, the star wouldn't shine.
No, it would just instantly collapse in on itself, crushing down into a dense, dark little point.
So something has to push back. We all learned in high school that it's nuclear fusion, but the actual quantum mechanics of how that engine works is just mind-blowing.
It truly is, because it's not straightforward. As gravity compresses the gas, it converts gravitational potential energy into kinetic energy, which manifests as heat. The core of a star like our sun reaches temperatures of about 15 million degrees Celsius.
Which sounds incredibly hot to us.
It does. But normally, hydrogen nuclei, which are positively charged protons, violently repel each other due to the electromagnetic force.
It's like trying to push the north poles of two extremely powerful magnets together. They desperately want to bounce away from each other.
Exactly. But the gravitational crush creates such intense heat and pressure that the protons are slammed together at velocities high enough to overcome that repulsion.
Wait, but even then, classical physics says they shouldn't actually be able to fuse, right? Like, the temperatures in our sun's core actually aren't hot enough to force protons to overcome that electromagnetic barrier.
You're absolutely right. In classical physics, it fails. The engine shouldn't work. It requires a quantum loophole.
Quantum tunneling.
Yes, quantum tunneling. In classical physics, a proton hitting that electromagnetic barrier is like a ball rolling up a steep hill without enough speed. It should just roll right back down.
It doesn't have the kinetic energy to crest the hill.
Right. But in quantum mechanics, particles behave like waves of probability. They aren't just solid little billiard balls.
So their exact position is a little blurry.
Exactly. There is an infinitesimally small but mathematically real probability that a proton simply tunnels through the barrier and instantly appears on the other side, fusing with the other proton.
Without ever actually going over the hill.
Yes. And because there are so many octillions of protons in the sun's core bouncing around, this statistically rare event happens constantly. They fuse to form helium. This is the proton chain reaction.
And that quantum tunneling is the exact mechanism that generates the engine's output. Because when those protons fuse into helium, the resulting helium nucleus actually weighs slightly less than the protons that went into it.
The mass defect.
Right. That tiny missing fraction of mass doesn't just vanish into nowhere. It is converted entirely into raw energy, following Einstein's famous E equals mc squared.
That is the output of the system, the conversion of mass into radiant energy. This energy violently radiates outward from the core, creating an immense outward thermal pressure.
So it's pushing back against the crush.
Perfectly. Look at the system state. You have the relentless inward crush of gravity, perfectly countered by the explosive outward radiation pressure of nuclear fusion. This is what we call hydrostatic equilibrium.
As long as the star has hydrogen fuel to feed the fusion engine, these two forces balance out.
The star remains stable. It shines. It keeps gravity temporarily at bay.
It is literally a localized, fiercely burning rebellion against the dark, crushing nature of the void. And this brings up a concept that I find so profoundly beautiful, and it connects directly to you listening to this right now. Every single piece of complex matter in your immediate vicinity,
Everything.
the calcium in your bones, the iron carrying oxygen through your blood, the carbon making up the cellular structure of the device you were using to listen to this, none of that was created in the Big Bang.
No, the Big Bang only gave us hydrogen, a little bit of helium, and a trace of lithium.
Right. Everything you hold precious, your own body, was assembled in the first few minutes of the universe as raw gas.
Yeah.
And then it was physically forged and transformed inside the hearts of these stellar engines.
It is the ultimate cosmic recycling program, driven entirely by thermodynamic gradients. This is the cycle of death and rebirth happening on a galactic scale.
Amazing.
The Stelliferous Era, this era we find ourselves in, it represents a temporary window of immense complexity. Energy flows out of these stellar systems, bathing surrounding planets in light and heat.
And that flow is what makes life possible.
Exactly. That continuous flow of energy, that steep gradient between the hot sun and the cold void of space, is the only physical reason that complex chemistry, weather systems, biology, and ultimately conscious life can exist.
Yeah.
Life fundamentally requires energy moving from a high state to a low state.
The stars are just the batteries providing that flow.
But batteries eventually rupture. When the most massive stars, the ones burning the hottest and the fastest, reach the end of their fuel, they don't just quietly turn off.
They go out with a bang.
A massive one. They undergo core collapse supernovas. They explode with the force of entire galaxies, and in doing so, they scatter all those newly forged heavier elements, the oxygen, the carbon, the iron, the gold, out into the interstellar medium.
And then that enriched stardust cools down, it clumps together under gravity again, and it forms the next generation of stars. And critically for us, it forms rocky planets like Earth.
If we connect this to the bigger picture, it is a massive, multi-billion-year feedback loop. Stellar birth enables localized complexity. Stellar aging reshapes the thermodynamic environment. And stellar death violently redistributes the necessary raw materials for the next iteration of the cycle to begin.
It's a beautiful system.
It is, and this is the absolute non-negotiable constraint of the system. This era is finite.
It can't go on forever.
No. Stars consume nuclear fuel. They permanently convert hydrogen into heavier elements. And the universe has a strictly finite amount of available hydrogen. The fuel gauge is slowly but irreversibly moving toward empty.
Which brings us right to our own front door. We've talked about the macro scale, but where does our local system, our own sun, fit into this grand thermodynamic arc? We rely on it for every single thing, our seasons, our agriculture, the liquid state of our oceans.
But it is bound by the exact same systemic rules.
It's a finite engine.
It is entirely subject to the same equations. Our sun is just one of at least 200 billion stars in the Milky Way galaxy, which itself is one of an estimated 2 trillion galaxies in the observable universe.
That scale is just dizzying.
We are currently bathed in the light of countless scattered islands of stellar engines. But focusing specifically on our local system, the sun formed roughly 4.57 billion years ago from the debris of previous supernovae.
So it's middle-aged.
Right now, it is sitting comfortably in the main sequence of its life cycle. It is middle-aged.
And the data point on how much fuel it is actually burning just to maintain the equilibrium, it is staggering. It's really hard to wrap your head around. Our sun is currently fusing hydrogen into helium at a rate of 600 million tons every single second.
600 million tons per second. Let's really contextualize that mass. That is the equivalent of taking the entire mass of the Earth's oceans and converting it to pure radiating energy every few minutes.
Every few minutes, the whole ocean.
Continuously, without a single pause, for over 4.5 billion years. And based on its total mass, it has enough hydrogen reserves in its core to maintain this specific hydrostatic equilibrium for roughly another 5 billion years.
Okay, but the tank will run dry. The hydrogen in the core will eventually be exhausted. So what happens to the systemic equilibrium when the engine starts to fail? Here's the thermodynamic paradox that always tripped me up when I first learned about this.
What's that?
As the core runs out of fuel and the fusion engine stops, you would intuitively think the star would cool down. The fire is going out, right? So it should get colder, but it actually does the exact opposite. It gets radically hotter.
It is deeply counterintuitive until you apply the system's lens to it. When the hydrogen in the core is finally depleted, that outward radiation pressure drops to zero.
The pushback is gone.
Exactly. That delicate equilibrium we talked about is shattered. Gravity, which has been pulling relentlessly on the star for 10 billion years, instantly regains the upper hand. The core of the sun, which is now mostly composed of helium ash, begins to collapse rapidly inward under the immense weight of all those outer layers.
And as it collapses, it's trading gravitational potential energy for kinetic energy. It's compressing.
Yes, the core collapses, and as the density skyrockets, the temperature spikes dramatically. It is essentially using its own gravitational death spiral to ignite a secondary engine.
A backup generator.
Sort of, but a much more violent one. The temperature inside the collapsing core will rise until it reaches a terrifying threshold of 100 million degrees Celsius.
Wow, from 15 million up to 100 million.
Right, and at that extreme temperature, a brand new, far more energetic fusion process is triggered. Now, the helium nuclei, which have 2 protons each and therefore repel each other with vastly more electromagnetic force than hydrogen did, they can finally overcome their mutual repulsion.
Because the core is so dense and so violently hot that they are literally forced together.
The star basically begins burning its own ash. This is called the triple alpha process, where 3 helium nuclei fuse together to create carbon-12.
And the second phase of the engine has 2 massive consequences. One is the creation of that carbon-12. And we really can't gloss over how crucial that is.
We absolutely cannot. Carbon-12 is the fundamental building block of complex covalent chemistry. It is arguably the most vital element for life as we understand it.
Because of how it bonds.
Yes, its unique ability to form 4 stable bonds allows for the creation of DNA, proteins, and the complex molecular chains required for biology. Every single carbon atom currently sitting in your DNA, every carbon atom in the wood of the floorboards beneath your feet was produced in the suffocating heart of a dying star during this exact desperate phase of stellar evolution.
That is the beautiful, life-affirming part of the system. The fact that stellar death creates the components for life. But the terrifying part is the immediate local consequence for us, for Earth.
The red giant phase.
Right. Because when that helium fusion kicks in, it doesn't just gently warm things up. It releases so much violent energy that it completely halts the stellar collapse. And the sudden outward pressure forces the outer layers of the star to swell monstrously outward.
This marks the beginning of the sun's life as a red giant. Because the outer layers are pushed so far away from the core, they actually cool down, which shifts their light spectrum from yellow to a deep, angry red.
Hence the name.
Right. But the sheer scale of this physical expansion is entirely catastrophic for the inner solar system. The fiery, tenuous surface of our star will expand outward, completely swallowing the orbit of Mercury.
So Mercury's is just gone.
The planet will simply be incinerated. Then the solar envelope will push further out, vaporizing Venus, and ultimately the surface of the sun will encroach upon our own fragile world.
It is deeply haunting to picture. I mean, if you try to imagine that distant future, and if any descendants of humanity or whatever post-biological life exists, then are still around in this solar system, someone or something is going to experience the very last perfect day on Earth.
It's a sobering thought.
Because as the sun swells into this red giant phase and physically fills the entire sky, the thermodynamic gradient between the Earth and the sun will just collapse. The planet will simply bake.
Temperatures will rise exponentially.
The oceans, every single drop of water on Earth, will boil away into superheated steam. The kinetic heat will agitate the molecules in our atmosphere to such extreme velocities that Earth's gravity will no longer be able to hold on to them.
They'll reach escape velocity just from the heat.
Exactly. The atmosphere will just bleed off into the vacuum of space. The Earth will be completely sterilized, scorched into this barren, tidally locked rock, orbiting inside the outer atmosphere of a dying star. All memory of the biosphere here will just fade.
It is an inescapable reality of the physics. The Earth is a temporary haven. Long after the oceans have boiled and the atmosphere has been stripped away, the sun will continue its long, uneven decline.
Because the helium burning doesn't last as long as the hydrogen burning.
No, it's very unstable. It will cause the star to pulsate violently, and eventually it will shed its outer layers entirely into deep space. This creates a really beautiful, expanding shell of illuminated gas called a planetary nebula.
We've seen pictures of those from Hubble and Webb. They're stunning.
They are, but what is left behind when that gas clears? The core will have finally run out of all usable fusion fuel. It can't get hot enough to fuse carbon. Gravity will crush it down one last time.
And it doesn't become a black hole, right?
Yeah.
Because our sun doesn't have enough mass for that. So what physically stops the collapse this time if there's no more fusion engine?
This is where we leave classical physics behind entirely and enter the realm of quantum degeneracy.
Okay, let's break that down.
The core collapses until the electrons themselves are squeezed so tightly together that they are forced into the same quantum states. But there's a fundamental law of quantum mechanics called the Pauli exclusion principle.
A Pauli exclusion principle.
Yes. It dictates that no two identical fermions, like electrons, can occupy the exact same quantum state simultaneously. Because they cannot be squeezed any closer together, they exert a massive, rigid, outward pressure.
It's not a thermal pressure anymore.
No, this is called electron degeneracy pressure. It is not heat holding the star up anymore. It is the fundamental refusal of quantum particles to share physical space.
And the remnant that is supported by this quantum pressure is a white dwarf.
Correct. What remains at the heart of that nebula will be a faintly glowing, incredibly dense ember. All that is left of our magnificent life-giving sun will be a white dwarf.
And how big is that?
It will be roughly the physical size of the Earth. So it possesses less than a millionth of its current volume, but it retains about half of its original mass.
So the density is just off the charts.
A single teaspoon of white dwarf matter would weigh several tons. It will emit no new energy, the engine is off. It will simply sit there, radiating its residual trapped heat out into the cold universe, cooling down over billions of years. This is the destiny of almost all the stars you see in the night sky.
So our brilliant sun ends up as a cooling, ultra-dense lump of cosmic coal, basically, roughly the size of the planet it once nourished. It is a profound system shutdown.
It is the end of our local system's active phase.
But as we look past the death of our own sun and our own local system, we realize that not all stars burn through their fuel quite so recklessly as ours does. Here's where it gets really interesting, because the universe actually has its ultimate survivalists, the red dwarfs.
Yes, the red dwarfs. As we move through the eons ahead, the massive, bright blue and white stars will live their short, furious lives and explode as supernovae. The medium-mass stars, like our sun, will swell into red giants and eventually fade into white dwarfs.
Then the raw materials to make new ones will run out.
Exactly. The interstellar gas clouds will be exhausted. As the rate of new star formation plummets towards zero, there will be only one type of active star left to illuminate the universe in its extreme old age.
The frugal stars. And we have a perfect local example of this right next door, Proxima Centauri. It is our absolute closest stellar neighbor, only 4.2 light years away. But it is so incredibly dim that if you walk outside tonight, you cannot see it.
You can't even see it with a standard pair of binoculars.
In fact, it barely stands out in deep field photographs taken with professional telescopes. Proxima Centauri has only about 12% of the mass of our Sun. It is 18,000 times less luminous, and its surface temperature is a relatively chilly 4,000 Kelvin.
Let's view this through our system's thinking lens. Because red dwarfs are so diminutive, the gravitational pressure on their cores is much lower than in larger stars.
So the crush is weaker.
Therefore, the core temperature is lower, and the thermodynamic burn rate, the rate of that quantum tunneling we talked about, is exceptionally slow. They're sipping their hydrogen fuel rather than gulping it down like our Sun does.
But there is a second crucial systemic advantage they have, right?
Yes. In a star like our Sun, only the hydrogen directly in the core is available for fusion. The outer layers just press down, they don't mix, but red dwarfs are entirely convective.
Meaning they act like a boiling pot of water.
Exactly. The plasma physically circulates from the core all the way to the surface and back down again. This constant churning means a red dwarf drags fresh, unburned hydrogen from its outer layers directly down into the core and brings the helium ash up to the surface.
So it's basically stirring its own fuel tank.
Yes. It utilizes 100% of its available mass for fuel, whereas our Sun only uses a tiny fraction. This combination of a slow burn rate and total fuel efficiency gives red dwarfs lifespans not of a few billion years, but of trillions of years.
Trillions. Just think about the implication of that timeline for a second. If conscious, intelligent life manages to survive into the deep, deep future of the universe, long after the Milky Way has collided with Andromeda, long after stars like our Sun have completely burned out, where will they go?
They will have very limited options.
You can easily imagine our incredibly distant descendants, or some completely alien civilizations, systematically migrating across the decaying galaxy to these red dwarfs. They would have to build their orbital habitats or Dyson spheres incredibly tight around these tiny dim stars just to capture the last fading embers of usable energy in the cosmos.
It's a total cosmic downsizing.
It would be exactly the same dynamic as our ancient ancestors crowding closely around a sputtering space heater or a dying campfire on a freezing winter night, just trying to stave off the dark and stretch out the universe's utility bill for a few more millennia.
That campfire analogy is perfectly apt. Red dwarfs will be the absolute last oases of warmth in an increasingly cold, dark, and hostile void. Life, which fundamentally requires thermodynamic gradients to function, will have no choice but to huddle around them.
But even they don't last forever.
No. Even this extreme conservation of energy is no absolute defense against the laws of physics. The arrow of time is inescapable. The second law of thermodynamics cannot be cheated. Proxima Centauri might live for trillions of years, but its fuel supply is still strictly finite.
The tank is huge, but it still has a bottom.
Exactly. Roughly 4 trillion years from now, even Proxima Centauri's deep convective reserves of hydrogen will finally run out. And because it lacks the requisite mass to ever trigger the secondary helium fusion like our Sun did, there will be no red giant phase.
So no violent expansion.
No. It will simply slowly contract, the fusion engine will quietly shut down, and it will fade directly into a white dwarf.
And when the last red dwarf in the universe finally exhausts its fuel and winks out, the universe crosses a massive, irreversible threshold.
Yeah.
The age of starlight, the Stelliferous Era, officially ends. The lights go out.
This initiates the next major phase of cosmic evolution, a period characterized by deep systemic decay. This is the Degenerate Era. Based on our current cosmological models, we predict this era will begin roughly 100 trillion years from now.
100 trillion years. It is almost impossible to hold that number in your head. Our universe is only 13.75 billion years old right now. 100 trillion is an ocean of time. But what does the system actually look like in this state? If the stars are gone, what is actually left out there?
The system state shifts fundamentally from active energy generation to passive energy dissipation. The universe becomes entirely dominated by stellar corpses. The actively fusing, glowing stars are gone. What remains is a sprawling graveyard of remnants.
White dwarfs we mentioned.
The white dwarfs, the ultra-dense neutron stars, and the black holes. Because the interstellar gas clouds have been entirely depleted or locked away in these remnants, there is no longer sufficient raw material or ambient energy to ever ignite a new star.
The engine-building factory is closed forever.
The luminous, visible macrostructure of the universe fades away into total blackness. Usable energy becomes increasingly diffuse, trapped, and scarce. To a human observer, the universe would appear dark, bleak, lifeless, and utterly desolate.
But the physics doesn't stop.
No, from a physics standpoint, the system goes on. Things are still happening, just on much, much slower timescales.
And inside that darkness, we have things like black dwarfs. I love this concept because it sounds like something out of a fantasy novel, but it is pure, hard physics. A black dwarf is essentially the final evolutionary stage of a white dwarf.
Yes.
It's a dark, ultra-dense, decaying ball of degenerate matter. It is the ultimate cold ash of a star. The engine has been off for so long that all the residual heat has finally radiated away into the vacuum. But what is totally fascinating to me is the cooling time.
It takes a very long time.
It takes a white dwarf so long to bleed off its heat and stop emitting any light or thermal radiation that at almost 14 billion years old, our universe is currently completely devoid of them. The universe is literally too young to contain even a single black dwarf.
That is a brilliant illustration of the timescales we are dealing with here. If we connect this to the bigger picture, the onset of the Degenerate Era perfectly illustrates the thermodynamic incentive architecture of the entire cosmos. The fundamental overriding law of the universe is that it naturally and inescapably evolves toward higher entropy.
Okay, let's clearly define entropy here, because it often just gets thrown around in pop science as a synonym for messiness or disorder,
Yeah.
like a messy room.
That is a vital distinction to make. Entropy is often colloquially called disorder, but in statistical mechanics, it is more accurately a measure of the number of specific ways a thermodynamic system can be arranged. It's microstates.
Right.
More practically, for our purposes, it is a measure of how spread out, diffuse, and unusable energy is within a closed system. A hot star in a cold vacuum is a low entropy state because the energy is highly concentrated. There is a steep gradient, and that gradient can be tapped to do useful work, like powering a biosphere.
The energy is useful.
Yes. But heat naturally flows from hot to cold. As the star radiates its energy into the void, the energy spreads out, the gradient flattens. Entropy increases.
And you can't get that heat back into the star.
Never. Stars temporarily fight against entropy locally by using gravity to concentrate energy and create highly ordered structures, but they are fighting a losing battle against the overall macro system. In the Degenerate Era, the universe is definitively winning that battle. Everything is cooling down. Everything is spreading out. The gradients are vanishing.
So even these dense little ashes, these black dwarfs floating out there in the dark, they aren't permanent either. The system doesn't just pause there.
No, the system does not pause. And this is where the physics leaves the macroscopic realm and becomes deeply profound on a subatomic level. Based on our current understanding of fundamental particle physics, specifically guided by the frameworks of grand unified theories, or GUTs, we predict that matter itself is not an eternal construct.
Wait. We are taught in school that matter cannot be created or destroyed.
In standard low-energy, everyday chemistry, that holds true. You burn a log in a fire, the matter isn't destroyed, it just changes state into smoke, ash, and heat. The protons and neutrons themselves remain intact.
Right.
But grand unified theories seek to mathematically unite three of the fundamental forces, the strong nuclear force, the weak nuclear force, and electromagnetism, into a single force at extremely high energies. And one of the key unavoidable mathematical predictions that falls out of these GUT frameworks is baryon number violation.
Baryon number violation. What does that mean for the stuff we're made of?
In simple terms, it predicts that the proton, the fundamental building block of the atomic nucleus, the anchor of all physical matter, is not perfectly stable. It has a half-life. It is theorized that the matter inside these black dwarfs, which will represent some of the very last concentrated clumps of baryonic matter in the universe, will eventually decay.
So you're saying that if you wait long enough, matter literally deletes itself from the universe. Look at your hand right now. The carbon, the oxygen, the physical structure giving you shape. Physics suggests that eventually the very glue holding the subatomic particles of those atoms together will just give up. Your hand won't just turn to dust. The dust itself will cease to be matter.
That is exactly the implication. Over unfathomable stretches of time, the protons will spontaneously decay into lighter subatomic particles like positrons and pions, which will then immediately annihilate or decay further into pure photons. The protons, neutrons, and electrons will literally evaporate away into the void as diffuse radiation.
How long does this take? Because we obviously haven't seen a proton decay in a laboratory.
We haven't, which tells us the half-life is unimaginably long. Current experimental bounds place the proton half-life at greater than 10 to the 34th years. That is a 1 followed by 34 zeros.
It's absurdly slow.
The processes governing proton decay are so incredibly slow that they are entirely irrelevant to the current Stelliferous Era. But in the Degenerate Era, time is the one resource the universe has in infinite abundance. Over trillion year timescales, the probable outcome becomes a certainty.
Matter evaporates.
Eventually, there will not be a single atom of physical matter left in the entire cosmos. No rocks, no dust, no dead planets, no black dwarfs. The rich, structurally complex cosmos we see today will be reduced entirely to wandering, highly diluted particles of light photons and the extreme gravitational sinkholes of black holes.
That is just, it's chilling. A universe completely devoid of physical, tangible matter. But what about those black holes? They are the ultimate gravitational traps. Nothing escapes them, not even light, so surely they stick around to anchor the void.
Intuition suggests they would, but even black holes are subject to the relentless, overarching laws of thermodynamics. They do not last forever either.
How is that possible?
Thanks to the groundbreaking theoretical work of physicists like Stephen Hawking, we know that the universe does not allow for perfect, permanent traps. Black holes actually leak energy over time.
This is Hawking radiation. But how does something escape a black hole if the gravity is so strong that the escape velocity is faster than the speed of light? It sounds like a paradox.
It requires an understanding of quantum field theory. Space is never truly empty. Even in a perfect vacuum, quantum fields are constantly fluctuating. These fluctuations briefly manifest as pairs of virtual particles, a particle and its antimatter partner popping into existence, borrowing energy from the vacuum, and then instantly colliding and annihilating each other, returning the energy.
So they just fizz in and out of existence everywhere.
This happens everywhere all the time. But Hawking realized that if this virtual particle pair pops into existence right exactly on the boundary of a black hole's event horizon, something entirely different happens.
The edge of the hole.
Yes. The extreme tidal gravity can pull one of the particles into the black hole, while the other particle is thrust outward into space, escaping the gravitational pull before they can annihilate.
But the universe demands an accounting of energy. You can't just get a free particle flying out into space from nothing.
Exactly. To balance the thermodynamic ledger, the particle that falls into the black hole must have negative energy relative to the outside universe. When it falls in, it effectively subtracts a tiny fraction of mass from the black hole. Meanwhile, the particle that escaped becomes real, carrying positive energy away.
So the black hole is slowly bleeding its mass away through these quantum particles.
This continuous quantum mechanism is known as Hawking radiation. Because they are constantly leaking this radiation into space, black holes very slowly lose mass. They are evaporating.
I really want to try to convey the sheer magnitude of the time scale we are talking about here for the last supermassive black holes to evaporate, because they are huge and the leak is incredibly slow. The number given in Professor Cox's source material is 10 to the 100th years. That is a 1 followed by 100 zeros. It is known as a googol.
10,000 trillion years.
It is a number so spectacularly large that the human brain, which evolved to track the seasonal migrations of antelope, simply has no cognitive architecture to comprehend it.
We just can't visualize it.
The analogy Professor Cox uses to try and ground this is brilliant. Imagine you wanted to count up to that number, 10 to the 100th, and let's say you decide to use atoms to keep track, like beads on an abacus. You take one single atom from somewhere in the universe to represent 1 year past. If you did that, there literally aren't enough atoms in all the stars, all the planets, and all the galaxies in the entire observable universe to even get close to that number. You would completely run out of atoms in the universe long before you reach 10 to the 100th years.
That perfectly illustrates the depth of deep time. And yet, despite our inability to intuitively grasp it, the universe will mathematically experience every single one of those years. The supermassive black holes sitting at the centers of dead galaxies will slowly, agonizingly bleed their mass away into the void via Hawking radiation.
And as they lose mass, what happens?
As they lose mass, they shrink. And as they shrink, they actually get hotter and evaporate faster until finally they vanish in a final sudden flash of high-energy gamma rays. And when that unimaginable expanse of time has passed and the very last black hole has evaporated, the universe will finally reach its ultimate permanent state.
The end of the line.
This is known in astrophysics as the heat death.
You know, heat death sounds so incredibly violent. If I just hear that term, I picture everything burning up in a massive inferno.
Yes, it is a significant misnomer that often confuses the public. Heat death is not an explosion. It's not a fiery collapse or a sudden incineration.
It's the opposite.
In strict thermodynamic terms, heat death means the death of heat. It is a state of absolute maximum entropy. It means that the entire universe has reached total thermodynamic equilibrium. All the usable energy gradients, those vital differences in temperature that allow energy to flow, work to be done, and complex systems to exist, they have completely and permanently disappeared.
So what is actually left in the physical space of the universe at that point?
The universe will consist entirely of a highly diluted, almost infinitely expanding sea of light, just scattered solitary photons and perhaps some neutrinos and electrons that never manage to annihilate.
Just a thin soup of particles.
And because the spatial fabric of the universe is continually expanding, those solitary photons are constantly being stretched out. Their wavelengths become longer and longer, redshifting deeper into the radio spectrum. As their wavelengths stretch, their energy drops. They will all tend toward the exact same microscopic temperature, cooling infinitesimally close to absolute zero.
So it's perfectly uniform. Everywhere you go, across the entire infinite stretch of the cosmos, it is exactly the same cold, empty, featureless void.
Exactly. And because there are absolutely no temperature differences anywhere, no hot stars, no cold planets, no gradients of any kind, no energy can flow from a hotter area to a colder area.
And without flow, nothing happens.
Without that flow of energy, without that gradient, absolutely nothing can happen. No engine can run, no organized activities physically or chemically possible. Once the last remnants decay, the last black holes evaporate, and everything reaches the exact same base temperature, the active story of our universe finally concludes.
It's finally stable.
For the first time since the Big Bang, the universe becomes truly permanent and unchanging. Entropy stops increasing because the system simply cannot get any more disorganized. The state space has been fully maximized, nothing happens, and it keeps not happening forever.
That brings up a concept that honestly breaks my brain a little bit when I try to sit with it. If literally nothing is happening, and everything is perfectly uniform and identical everywhere, you lose the ability to measure time.
You do. Time loses its meaning.
Because time itself fundamentally relies on change. A clock only works because the hands move from one state to another. A brain only tracks time because synapses fire in a sequence. If a cosmic era is completely perfectly unchanging, with no events to mark a before or an after, then time, as a functional, measurable physical concept, ceases to exist.
That is an incredibly profound and accurate deduction. You can no longer measure the passing of time because there are no events to mark it, there are no changing states. A trillion years in the heat death is physically indistinguishable from a single second. The cosmos becomes vast, cold, desolate, and frozen in an eternal equilibrium. The fundamental, inescapable laws of physics dictate that the active cosmos will die, and any possibility of biology, thought, or life will be permanently extinguished.
So what does this all mean? We started this deep dive talking about a crisis in perception. And the core of that crisis is that because we measure reality against our own microscopic human lifespans, we naturally assume the universe is a permanent, stable structure. We assume the stage will always be here for the play to continue.
But it won't.
A rigorous, systems-level analysis forces us to confront the fact that everything we see, everything we know, and everything we are is just a long, slow, thermodynamic evolution toward total stillness.
The crisis is mistaking a transient phase for a permanent reality. When you shift your perception from momentary, localized stability to the long-term macrosystem behavior, you realize that stars, galaxies, and life itself are simply temporary phenomena.
They are fleeting.
They're fleeting eddies in a river flowing inevitably toward the sea. We exist within a very rare, phenomenally brief window of cosmic history where the energy flowing through the system, that thermodynamic gradient, is strong enough to allow for complexity, heavy chemistry, and biology to emerge.
I think it's very easy to look at that timeline. 10 to the 100th years of cold, featureless nothingness compared to our tiny microscopic window of light, and feel a crushing sense of nihilism.
It's a very common reaction.
It's easy to feel completely insignificant, like human existence, all our art, our history, our science doesn't matter at all in the face of that overwhelming eternal void.
It is a natural human reaction to vast scales. But the source text and the system's perspective itself offers a very profound philosophical synthesis to counter that nihilism. We are not insignificant just because we are mathematically temporary. In fact, our strict transience makes our existence infinitely more remarkable. We are highly complex, incredibly fragile structures riding the long wave from order to disorder. We are made of star stuff, governed by the laws of quantum mechanics and thermodynamics. Life is the exact, intricate mechanism by which the universe has developed the capacity to observe itself, to analyze its own mechanics, and to understand its own eventual fate. even if only for a brief instant in the grand timeline.
I absolutely love that framing. When we build probes like Voyager and send them out beyond the edge of our solar system, carrying gold records of our music and voices, or when we launch the James Webb Space Telescope a million miles into the dark to peer back at the oldest, most ancient galaxies, we aren't just humans doing isolated science.
We are part of the system.
We are literally the universe acting out its own fleeting moment of self-awareness. We were the cosmos waking up, looking in the mirror, mapping its own architecture, and trying to understand its own reflection before the lights eventually go out.
Precisely. We occupy a dazzling, brilliant instant in infinite time. The universe is a system that allows for localized beauty and staggering complexity, precisely because it is expending its energy to do so. The fact that the universe will end, that the thermodynamic engine will eventually seize up, does not negate the grandeur, the depth, and the beauty of the system while it is actively running.
It enhances it.
In fact, fully understanding the mechanics of the end only amplifies the profound rarity and the preciousness of the present moment.
That is the phenomenal grounding place to wrap up this analysis. The universe might be temporary, but it is spectacularly beautiful while it lasts. Thank you for joining us on this edition of Crisis in Perception. Our goal here is always to rigorously examine how systems shape our beliefs and to provide you with the mental frameworks and physical tools to see reality a little more clearly.
It's been a great discussion.
Just a bit of housekeeping before we go. This project is totally free and publicly accessible because we strongly believe these macro perspectives should be available to everyone, regardless of academic background. But if you value this kind of deep systems-level analysis and you want to support the time, the extensive research, and the tools that go into making these deep dives possible, you can become a supporter on our Patreon. We would greatly appreciate it.
We really would.
Also, if you want a visual breakdown of the massive cosmic timeline we just discussed, from the primordial era all the way to the heat death, check out the shorter mini-explainer video. We've linked it right down in the description for you. And finally, we want to hear from you. Please like the video, subscribe so you don't miss our future deep dives, and drop a comment below with books, scientific concepts, or massive societal systems you'd like us to pull apart and explore next.
And this raises an important, deeply philosophical question to leave you with, building directly on everything we've explored today. If the ultimate, inescapable fate of the universe is a featureless, infinite sea of photons, sitting infinitesimally close to absolute zero, a thermodynamic state that effectively erases all physical traces, all structures, and all memory of our existence, does the abstract, mathematical, and historical truth of our having existed vanish as well? Or is the simple fact that you are sitting here right now listening to this, processing these complex ideas, and understanding the architecture of the cosmos, a permanent, indestructible record that is somehow etched into the fundamental fabric of reality, existing entirely outside the rigid bounds of physical time and thermodynamic decay?